Okay, sorry, let's try that again. So basically what we did in the lab today is you measured your maximum absorbance and you measured the wavelength that that happens at, okay? So that gives you kind of an idea of what type of light you're absorbing most of with each of these compounds. So if we look at the copper sulfate, just looking at your data, I'm going to average these a little bit here. Is that the actual average, 793? Okay, so the average between the two groups here was about 793 on the copper sulfate for the wavelength of maximum absorbance, and that's going to be in nanometers. Pretty sure that's what it was measuring in. And then the absorbance of that wavelength was right around, really pretty close to 1. So I think if you average those out, you're going to end up with something like 0.99 for the absorbance, okay? Which is right around where we wanted it to be. The copper nitrate, those were really close, actually. So the wavelength of max absorbance there is going to be around, and actually I think maybe for the copper nitrate, what I told the groups was find where the absorbance hits 1 and then measure that wavelength. So it's good that we got wavelengths that were close to one another. We're right at 750 or so on that. Okay, and the absorbance of those wavelengths is 1. I may tomorrow, after checking, I may tell you to adjust that just a little bit, but it's going to be close to that, okay? The zinc nitrate and the zinc sulfate, the absorbance at both of those wavelengths is essentially 0, okay? And that kind of makes sense because both of these were colorless compounds, right? And then the iron nitrate and the iron sulfate, those are a little bit further. Well, actually, the iron nitrate looks pretty good. That's right at 393, 394, somewhere in there for the maximum absorbance. And we're somewhere around 1.2 for the absorbance at that wavelength. It's not bad. I am not sure what happened with the iron sulfate, so we might just have to strike that data a little bit. Yeah, although that's... Oh, okay, all right. Sorry, I'm reading this wrong. 395 versus 396. Those are actually pretty close. So the wavelengths are good. We're right around 390, 395, 396, somewhere in that range, okay? And the absorbance there is about 1.4, okay? So what you might notice here, and what I was hoping that we would notice, is a couple of things. First of all, did it matter too much whether the copper was connected to sulfate or nitrate as far as its absorbance and wavelength data? It seems to have maybe made a little bit of difference. I mean, we could pretty easily chalk that up to experimental error, I would say. If you look at the iron, it's even more pronounced, right? These are really close to one another as far as the wavelengths and the absorbance data. I guess the absorbance data is a little bit closer for the copper. Point is, it doesn't seem to matter too much. Doesn't seem to matter too much if it's a sulfate or a nitrate, okay? And the zinc is completely colorless with nitrate and with sulfate. So what does that ultimately tell us about, and actually this is step 4 that we're answering right now, okay? So it says, look at the different plots. Can you identify the chemical species doing the absorbing? Is it the metal ion, the polyatomic ion, or both? It looks to me like it's the metal ion, right? Okay? It's probably the copper and the iron. And the reason that we can identify that, you can just use the explanation we were just talking about to answer the second part of that question, okay? Does that basically make sense? Because the zinc is colorless with the nitrate and the nitrate and the sulfate are probably not the things that are causing the color. And again, because the copper sulfate and the copper nitrate, it doesn't seem to matter too much whether it's with a sulfate or a nitrate for either the copper or the iron. Their absorbency numbers are still basically about the same, okay? So, the copper is the thing that's turning blue in the solution. We kind of already knew that, right? And the iron is the thing that's turning the solution a little bit reddish yellow. All right? So then step 5, engage in whole class discussion to answer the following questions. Well, we're not here as a class, so you're just going to have to pretend. But the first question here, why do we want to use a particular wavelength when we're determining the absorption of a particular chemical species? Is it important to measure absorbance for all wavelengths for 400 to 700? Okay, so they told us in the lab to measure from 400 to 700, which we essentially did, but you had a nice computer program that basically did it all for you all at once, right? So that you got a graph and you could see the data from 400 to 700. So the question is, why is it even important to know where the maximum absorption is? Okay? And the reason why, you might have a tough time actually answering that question, but let me show you something here. So let's say you've got a graph like this, okay? So this graph is showing the curve, basically the absorbance versus the wavelength, okay? Now notice your peak wavelength is up here around, and you kind of get a dip. So you've got 2 peaks here a little bit. But your maximum absorbance is around a wavelength of 540 or so, somewhere in that range. Okay? Now, let's say that instead, let's say that I'm measuring at 500 instead. Okay? So this is my absorbance. I'm measuring my absorbance at 500 nanometers wavelength. What happens if there's a little fluctuation in the wavelength that's being measured by the instrument, and all of a sudden it starts measuring at 480 instead of 500? Well, that drastically affects my absorbency, right? Because this thing is a really steep curve here, okay? So now I'm down here all of a sudden. That's a big difference, okay? But if I'm up here towards the peak, then there's really not nearly as much variation, okay? So you kind of want to be in that spot right at the peak, because if you're a little bit off as far as the detector and the wavelength it's measuring, it's not going to make as much difference as far as the absorbency that you're measuring. Does that make sense? So that's what we did today, is basically learning how would you find the peak absorbance, because that's what you really want to know when you're measuring. When you start doing the absorbance versus the concentration, you want to make sure you're measuring that at the correct wavelength. Okay? All right, hopefully that makes sense. And then the second question here, if you know the molar absorptivity of the copper sulfate at 630 nanometers, see, and that's why I think we may have to adjust a little bit, because I'm thinking 630 is really more of where we should have seen our peak, which I'm not exactly sure why that happened, other than some of those cuvettes were a little used. But, I mean, you guys are using the ones that were fairly clean, right? And you cleaned them off with the Kleenex first. I'm not exactly sure why we were getting a higher absorbance there. Other than maybe, I mean, the only thing I can really think of is maybe the cuvettes weren't completely clean. It's also slightly possible that maybe well, that wouldn't have made a difference in that direction. Or maybe the lab's wrong. I think what we'll probably do tomorrow, the nice thing about the data that you get when you measure this tomorrow, you can see where the peak is going to be. All right, so you can measure right at the peak absorbance. And so it's not as big a deal with the equipment we have to know exactly what wavelengths to set it at. Using the old ancient spectrophotometers that we've had here in the past, you have to set it for one particular wavelength, and then you're measuring the absorbance that wavelength. So that's when it would be really important. But with the equipment we have, it's not as important. Okay? But the question is, how could you determine a wavelength where the molar absorptivity is half of that simply by examining the absorption spectrum? Probably we'd need to look at the graph, right? Okay? So, and we have a graph here. Now this isn't the graph of copper, but using that as an example, I guess, actually, let me not use that as an example, because it's not even in the same units as far as the scale. But let's say we've got our absorbency over here, and we've got our wavelength, okay, and we've got a graph here, and the peak, you know, maybe comes at 6:30, and then it trails off from there. That's way prettier than that's ever going to look. But if our peak is here at 6:30, then we would need to basically look at our graph to figure out a place where the molar absorptivity is half of that. Now, there is another way to do it, and this is where I'm going to teach you Beer's law, okay? So if you look at Beer's law, oops, wrong one. Get rid of my X's here. Did I miss it? Okay, here it is. They had it bigger somewhere else. No? Just further. This is going to be a great video. That's the end. What the heck? Okay, this is it right here, but I know that it was bigger somewhere in this document. Yeah, I looked at the top, didn't I? Maybe I didn't go far enough. Possible. See, because oh, okay, it is up there. All right. So here is Beer's law. Okay. Now, Beer's law relates concentration. That's the C. Okay. It relates absorbance. That's the A. And it relates the path length, which is basically just the distance the light has to travel through the cuvette. This proportionality constant right here is related to the wavelength. Okay, so that's the wavelength is not specifically in Beer's law, but this proportionality constant right here, the wavelength has to be constant, and given that constant wavelength, you have a certain proportionality constant, right? Now, the proportionality constant and the path length are always going to be different depending on, you know, what you're using. Now, the cuvettes we're using should all have the same path length, okay? But it's a hassle sometimes to figure out exactly what that proportionality constant is, okay? So I guess ultimately the best way to answer that other question before we move on, so that I'm not confusing you too much here, really probably the best way is to look at the graph for extension question number 2, okay? Because I was thinking in Beer's law you could actually relate the wavelength to the absorbance, but in Beer's law you can't do that very well because it's a proportionality constant. It's not really just the wavelength, okay? But here, step 6, make sure to write down your understanding of the relationship between concentration, absorbance, and wavelength. That's where we're talking about Beer's law, okay? So basically, here's our strategy for tomorrow, okay? So Beer's law, instead of having to find the proportionality constant for this thing, which is, like I said, kind of a pain, what we can do is we can we can change the concentration of a known, okay? I'm not sure if that's the best way to show concentration. I guess they're using a C there. I'll put it in brackets to make it a little more obvious. Concentration versus the absorbance, okay? Turns out, if you keep measuring at the same wavelength every time, then you're going to have that same proportionality constant, okay? So this E stays the same, or this epsilon. If you keep the path length the same every time by using the same cuvettes with the same thickness, then your L is going to stay the same, all right? So then, if you look at this equation, A and C are actually directly related to one another. There's a direct relationship there, which means that as the concentration increases, so should the absorbance. Okay? So what we're going to do tomorrow, you've got your unknown back there. We're trying to figure out the concentration of the copper in that unknown. Okay? What you're basically going to do is you're going to measure the absorbance of a 0.4 copper solution, a 0.4 molar copper solution, a 0.2 molar copper solution, a 0.1, and a 0.5, I believe. Okay? With that, you're going to be able to make a graph of concentration versus absorbance, and then you're going to get a best fit line. Okay? Then what you can do, you're going to measure the absorbance of your unknown. Once you have a best fit line, all you have to do is trace over from the absorbance, trace down. That should give you the concentration of copper in your unknown. Okay? So simple as that. So once you figure out that concentration, then you can do the final calculations you'll have to do to figure out the mass percent of the copper in the brass solution, because you can work backwards from the concentration to figure out the number of moles of copper that you had in that solution. Then you can figure out, obviously, the number of grams you had of copper in that solution. And then once you do that, as long as you know the starting mass of your brass, if you know how many, I know it's funny, then as long as you know that starting mass, then you can obviously just compare that to the mass of the copper that was in your solution and figure out what percentage. Okay? Does that kind of make sense? And that's the basic strategy for what we're doing here. So Beer's law is useful to know, but we're not actually going to use it in the sense that we're not going to calculate this. Okay? The only way you could calculate this is if I gave you the epsilon for this particular chemical at this particular wavelength and at this particular temperature. Okay? Everything else you could figure out. You could get the path length. I think the path length is usually just measured in centimeters. But it's much easier to just do a concentration versus absorbance graph and then figure out where exactly our unknown falls on the graph, and then we can measure our concentration based on that. Okay? All right, so let me erase this. There's one other thing that we need to talk about, which is basically just, I don't think this will take too long, cereal dilutions. Do you know what I mean when I say cereal dilution? I'm not talking about when you put too much milk in your cereal. All right, so this is going to be in step 4, okay? By the way, step 3, I'm probably going to go ahead and put the 50 mils of distilled water into your beaker. And hopefully your brass will have dissolved by tomorrow. I'll see if I can get that to work. And then you're going to put that into a 100 milliliter volumetric flask that you have at your lab station, so you'll know exactly the volume of solution that you have there, all right? Yeah, and it's saying the excess nitric is supposed to dissolve the zinc and the copper metals in the brass. We'll see. I might have to put in a little bit more nitric tomorrow morning if it hasn't dissolved by the time I come in, but I'll take care of that. By the time you get in, your step 3 should be ready to go. All you'll have to do is dilute to 100 milliliters in your volumetric flask. Okay? Then the other thing that you're going to have to do tomorrow, fairly quickly at the beginning of class, is you're going to need to make, I'm going to have the 0.4 molar stock solution for you. Okay? And then you're going to have to dilute that and make a 0.2 molar solution, a 0.1 molar, a 0.05 molar, and a 0.025 molar solution. Okay? And so basically what you're doing is you're just cutting it in half each time that you do it. Okay? This is what's called a serial dilution. You may have done this in biology. It's not that complicated. All right? So you've got 10 milliliters of a 0.4 molar copper nitrate solution, and you need to figure out what volume is required to make 10 milliliters of 0.2 molar. It doesn't seem like that should be that hard, right? I mean, we're cutting the concentration in half, so what do we probably have to do? Yeah. Basically, if we want to make 10 milliliters of the 0.2, then we'll measure out 5 milliliters of the 0.4, add 5 milliliters of distilled water, right? Does that make sense? That'll make 10 milliliters of the 0.2, okay? So now the nice thing about that is that's going to leave us with 5 milliliters of this, right? Because we got 10 to begin with. We only used 5 of it to perform our serial dilution. So what you should end up with there is basically 5 milliliters. I'm not doing sig figs here, but 5 milliliters of 0.4, right? And then you use the other 5 milliliters of the 0.4 to make your 10 milliliters of 0.2, okay? So then you've got 10 milliliters of 0.2, but you're not going to end up with 10 milliliters of 0.2 because you have to dilute that to 0.1. So how would we dilute the 0.2 down to 0.1? Take out half and add 5, right? That would make 10 of the 0.1. Do the same thing again. Take out half and add 5 milliliters to make the 0.05. And then take out half, add 5 milliliters of distilled water to make the 0.025. That's pretty simple, right? So you'll end up with 5 milliliters of each one. You'll end up with 10 milliliters of the 0.025 at the end, okay? But 5 should be plenty because all you need is just enough to fill one of those cuvettes so you can measure the absorbance, okay? So basically what you're doing, ultimately, you're going to measure the absorbance at 0.4, the absorbance of the 0.2 concentration, the absorbance of the 0.1, the absorbance of the 0.05, and the absorbance of the 0.025. And then you should have enough points, data points, to give you a pretty nice graph where you can draw your best fit line. Okay? Now, number 5 here, I'm just going to talk about this for a quick second, and then we're done. They recommend not to make the light be passing through when the absorbance is at a range of 1 to 2. They recommend that you make it a little bit less than 1, all right? So what you want to do with your strongest concentration, the 0.4 molar, when you drop that into the spectrophotometer tomorrow, you want to make sure that you are measuring at a wavelength that gives you an absorbance of a little bit less than 1, okay? And I wouldn't worry too much about why that's the case. It's just kind of a technical thing where you're just going to get better data that way, okay? And they do try to explain a little bit here. It has to do with the fact that it's a logarithmic function, okay? But again, you don't necessarily need to understand that. You just need to understand this is what you have to do. Now, once you have figured out that 0.4, let's say that the 0.4 molar, I'm just going to hypothetically say that 0.4 molar gives you an absorbance of about 1 when you look at a wavelength of 670 nanometers, okay? The rest of the concentrations need to be measured at the wavelength of 670 nanometers, all right? In order for this graph to work, your wavelength has to stay constant. So whatever wavelength you measure your 0.4 molar at, you need to measure the 0.2, the 0.1, the 0.05, and the 0.025 at exactly that same wavelength, all right? Otherwise, you're messing with epsilon in that equation, and your line isn't going to end up being linear. Does that make sense? I know this is a lot of new stuff, so. Okay. So those are the basic things that I wanted you to know coming into tomorrow, just to make sure that you guys are ready to go. It doesn't take very long to get the data once you have those spectrophotometers calibrated and everything. So I don't think you're going to have any trouble getting your data tomorrow. The two things that are going to take a little bit of time, well, actually just the one thing really, is performing your serial dilutions. So you're going to have to take that 0.4 molar and get that diluted down fairly quickly. I will have volumetric pipettes for you guys so that you can do that exactly, because you want to make sure those concentrations are pretty exact, right, so that you get good graphs. That's the main thing that's going to take you a while. Once you have the solutions made, actually measuring the absorbance is very, very fast, okay? And then once you have that done, you can measure the absorbance of your unknown, and that's really all the data you need to collect in order to be able to complete the lab. All right? Sorry, that was kind of a long one, and hopefully it made sense. I feel like I was rambling every once in a while. But I guess we will see you guys in class tomorrow.